Hi everyone. For our second talk of the day, we'll have Mathieu Blanc, who is a postdoctoral associate at NYU Courant Institute, working with Shara Schmecht on deep learning for parameterization in climate models. And he received his PhD from École Normale Supérieure, ENS, in Paris.
Thank you. Thank you for being here. So I'm Mathieu, and I'm going to present a work called Interpretable Meta-Learning of Physical Systems, which we did with my PhD advisor, Marc Lelarge, during my PhD. So it's mostly on the machine learning side, but with targeted applications on physical systems. And so the topic here is going to be building adaptive models that can handle multi-environment data from physical systems. So the general topic is machine learning for physical systems. So as you all know, machine learning is very promising for many applications in physics, including climate and weather forecasts. So here you can see some applications in weather forecast and oceanography. And the topic that we are going to talk about is one challenge that we have to face when we learn physical systems, that is the variability of physical systems. So physical systems are not fixed, but they vary over time or over experiments. Here you have, for example, data from the ERA 5 reanalysis dataset, showing that, of course, the climate changes over years. And so if you're to learn a machine learning model, it has, in some sense, to adapt to the variability of the system, right? And so for physical systems, this is hard because data is typically very rare to acquire. So it's difficult to have a data set covering the whole variability of your system. And so another challenge is that when you do deep learning models tend to be uninterpretable because there are just black box models. And when we are learning physical systems, we'd like to have some interpretability in terms of physical parameters, for example. So here's an illustrative drawing of what the problem is for dynamical systems that vary over time. We have a trajectory of dynamical system with some data here in the past, on which we've trained, say, some machine learning model, which forecasts this blue trajectory here. Now, if our physical system is varying over time, what's likely to happen is that in the future, the new observations that you're going to have will follow some shifted distribution with respect to the past. And so your trained model on the past will not be accurate. And so what we would like to have is a way of adapting your trained model to fit those new observations at a cheap cost without retraining the whole model from scratch. So have some sort of adaptive model. So now let's see a mathematical framework for that on a simple example. Here I have a very simple physical system that is the temperature field in 2D between two bars, so satisfying here the Laplace equation. And so what an example of a variable physical system here is that, okay, so sorry, first, when we try to do machine learning, we want to learn a predictor of the state of the system, which is here the temperature y of x as a function of space. And we want to learn it from a data set D that you have from system. So now the system is variable, so what's likely to happen is to have some physical parameter phi, which is here the displacement of the bars, that will vary from one experiment to another. And so you want your machine learning model to be robust to that, otherwise you're not going to learn effectively. So let's see what happens if you do a naive machine learning model, train on those multi-experiment data set, that is a data set made of the data collecting during the different experiments with the different physical parameters. So assume that we have data from two experiments with some variability between the experiments, and you train some sort of machine learning model by regression here on the collection of these two data sets. Now, if you have at prediction time some observations of your new system, so it's the same system but with a slightly different physical parameter leading to a slightly different distribution, what you could do is just tune this the parameter of your model. But if we did only that, what we would learn is just a blurry prediction of the collection of all the data that we had, precisely because we have not modeled the variability of our data set. We have not incorporated in the model some parameter indicating that the data distribution would be slightly different from one experiment to another. And this is where meta-learning can come into play to help us handle those multitask data scenario. So I'm going to talk about that. So meta-learning is a paradigm that's gained much interest in the machine learning community, and especially in the deep learning community. And here's how it can be useful. So we have this multitask problem where our data set is made of several data sets with several, each data set T, the DT here, is collected from one instance of our physical system with a different physical parameter. So here, task is going to be a synonym for physical parameter or environment. And so instead of modeling the x to y relationship with a classical regression model, f of x theta, meta-learning adds another parameter, w here, that models precisely that extra degree of freedom of variability between the tasks or environments. And so here again, with this new parameter, we can train the model to minimize regression error here, but with this new parameter w that is adapted from task to task at each task. And so now if we have this new sort of model, at prediction time, we can just tune the task-specific parameter, that is w, and keeping theta fixed. Okay, so theta is the parameters of, say, a deep neural network. It's fixed after training, and at prediction time, we just adjust w to fit the observation of our new environment. So on our example, here's how it would go. So we have the multitask data set and yet another environment at prediction time. And here, as before, you train theta to minimize the prediction error on your data set, but you have also a parameter w that is adjusted at each task, for each task, to take into account the variability of each specific experiment. And now at prediction time, you just tune the w parameter to fit those new observations. And now that you have modeled this variability, you can hope to have some good generalization on this new experiment at prediction time. So that's basically the concept of multitask meta-learning. Now, all the question is how to compute this WT for each different experiment, right? Because I haven't specified that. And so when we're doing deep learning, the parametric model is a deep neural network, and a popular approach for modeling the task variability has been the MAML algorithm that is now pretty famous in the deep learning community. And so what MAML does is that it says that the variability of each task can be encoded in the parameter space of the neural network by an additive correction. So f of x theta w is just your neural network f of x theta corrected additively in the parameter space by some w. And so this kind of algorithm of architecture has known many successes in reinforcement learning, classification, many fields, and even recently in physical systems with the CODA architecture from a group in Paris. So a paper from Kirschmeyer and collaborators. But the drawback with such an architecture, so there are a few. First, it's very computationally challenging to train and to adapt because the parameter space of a neural network is, of course, of a huge size. Second, even once the neural network is trained, adapting the neural network is very costly for the same reason. And third, this method is not interpretable because the parameter space of neural network that you here adapt is not interpretable. So with these considerations in mind, we've tried to do something more interpretable and faster based on the following observations. So with mammal, since we are learning an additive correction in the parameter space of a neural network, well, by extending this reasoning, we could just try to linearize the neural network with respect to the parameter. And if we do that, we observe that the term that is specific to each task is just a linear or affine contribution in this equation. Also, in physical systems, the physical parameters that vary from one experiment to another can also often be found to be linear, just as in the equation above. So there's often a linear dependence. It's often always not, it's not always true, of course, but what we can hope for is to have a locally linear dependence in the task parameter, because since we're dealing with a multitask learning problem, all the tasks have some similarity. So we could argue that the physical parameters only slightly vary around some central value here, phi 0. So those two equations suggest that one good way to learn cheaply a multitask problem would be to postulate an affine or linear dependence of the statistical model with respect to this task parameter. And this is what we did with the architecture that we proposed, called CAML for Context Affine Multi-Environment Learning. We propose to model the output as a neural network that is task agnostic times a linear or affine task-specific contribution W. So based on the previous observations. And so by doing that, we have speed, because the linear structure allows us to make all the computations much faster, both at training and at prediction time. In fact, at adaptation time, so at when you want to tune W, it's just an ordinary least square regression that you want to solve, so you can do that in closed form, as opposed to gradient-based methods to optimize W. And finally, it's more interpretable. Actually, we have a result showing that when the physical system has the same structure of linear dependence with respect to the task parameter, the physical parameter, you can actually learn a mapping between the physical parameter and your learning parameter W. This is what you show in the paper. I'm not going to go into the details, but this result shows that this architecture is interpretable. So now let's see some applications on physical systems. First, on our simple 2D example from thermodynamics, here we have the error curves for train architectures as a function of the number of adaptation shots, which are the number of data points that you provide the model to adapt to a new task. And so as you can see, when the physical system here does exhibit some linear structure with respect to the physical parameters, because CAML mimics this dependence in the learning model, adaptation can occur at a much faster rate and with lower error. And you can see on the bottom the computational times. They are much lower for this simpler linear structure of CAML compared to the black box approaches that I presented before. And so here's here you can see an illustration of in the bottom row, no, in the center row, you can see the reconstructed physical system by CAML, learned from, so adapted from 50 shots. So with increasing perturbation, the estimation of the actual physical parameters in terms of the learning parameters of the learning model. And as you can see, when the perturbation of the bars on the left is small, that means that the physics is linear in the physical parameter. And you can see in the bottom row that the identification error is very low for CAML. So CAML is able to identify the physical parameters from the learning parameters, so showing the interpretability of the model. whereas the other approaches are not able to do that. So now let's see an illustration that I made in the last days to illustrate this model from a climate dynamics learning perspective. So in this example, we use a neural network to learn parameterization of the Burgers equations, so a very simple PDE, for which there are some small scale phenomena, and so parameterization is necessary if you want to simulate this PDE at small resolution. And so here on the animation, you have in red, no, in black rather, the high resolution simulation. In blue, the small resolution, the low resolution simulation. And in red is what the neural network corrects the blue simulation, so the parameterization. And at the dashed line here, the physical parameters of the dynamics abruptly change, okay? So we have a time varying dynamics with some varying physical parameters. On the left, the neural network is not trained on, does not model this variability in the physical parameters, and so cannot adapt to change of physical parameters. So as you can see, in the beginning, it manages to somehow parameterize and resolve the subgrid phenomena, but once the physical parameters changes, the neural network completely loses track of the dynamics, which you can see on the energy value being far from the true energy. Now, a meta-learning approach will model, for example, with camel. Here I implemented camel, so models the variability of the physical parameter, and in real time adapts the model to fit the physical parameters on the new observations. And so it's able to track the dynamics even if the physical parameters vary abruptly. So that's a kind of a small illustration of the model on a dynamical system on a typical, let's say, a typical climate forecasting problem of parameterization. So another field where we've experimented but less relevant is robotics. But actually, there are a lot of interesting connections between robotics and control and climate science. Here you have the goal is to learn the dynamics of a robot. So here's a robot arm, and you want to use this learned model to track a trajectory, a desired trajectory of the arm, which is in black here. And so here in gray is an analytic model that does not know exactly the dynamics because the dynamics here has friction and the analytic model ignores friction. So it's enabled to track the robot. And abruptly here, there's a new mass on the robot arm, making the analytic model completely losing track of the dynamics. Whereas if you train your neural network to learn friction and the full dynamics in an adaptive way, the control is going to be able to track the trajectory even if at some point you change the physical parameters. So, of course, another benefit is interpretability, which can be illustrated. I'm not going to go into the details here, but you have tracking curves, and on the bottom you have parameter identification curves showing that because our learning model camel here in red is interpretable, we're able not only to track the trajectory, but also to estimate the physical parameters that vary across time, whereas it's impossible with the other approaches. So we've made some experiments on the simulator of one robot that we had in INRIA, but here again it's robotics. But you can think of the same techniques being applicable to climate potentially, with some trajectory tracking and, thanks to the interpretability of the method, parameter estimation. So to summarize what we did here, we started from a complex black box vision of multitask learning model. And we said that, well, we can linearize this complicated expression that is postulated on black box papers to the first order. The zero order term would be ignoring the task variability, but the first order term we show is easy and cheap to learn. So it's kind of it can be thought as an easy first step when you want to learn a variable system. And if this first step doesn't succeed, of course, you can go to higher orders or to the full black box model. But our point is that you can learn efficiently with this cheap and simple first order approximation. Of course, when the data distribution deviates from a linearly parameterized physics, this is expected to work worse. So as a conclusion, what we've proposed is a multitask learning model for physical systems. And thanks to the linear structure of the problem, we're able to design a simpler architecture that leverages the structure, and by leveraging it, makes the learning and the interpretability of the model better. So it's computationally more uh, efficient, which can be very important in applications where you need to do the computations often, such as dynamical systems. And yeah, so it's very well suited for real-time applications because, as I said, ordinary least squares can be computed in closed form and online, meaning that it's basically inexpensive to adapt the model as time goes for each time step. And so that's it. If there are any questions, I'll be happy to try to answer.
Thank you. Very good presentation. I have a question. It's the prerequisite for use of this method is I should know the physical equation, right?
So it's not a requirement. You can use this method on any system, but the point is when you know that the system exhibits this structure, at least approximately, you expect this method that exhibits the same structure to work better and that and in an interpretable way, in the sense that you can estimate the physical parameters in terms of the learning parameters. But it's not a requirement. You can, in fact, in the in the example here, when the two bars are separated by a large space with a large angle, the physics is not like the perturbation of the system is large with respect to the normal position, and so the physical parameters is expected to be to intervene non-linearly, but yet the reconstruction is still accurate. I'm sorry?
Sorry. That means this method is can solve those nonlinear problem, right?
Yes, but it's specifically designed to work well when you know or where you expect the physics to be linear in some physical parameter that varies.
Okay, thank you.
Yeah, thank you so much for your talk, Mathieu. I just had a out of curiosity, because maybe I didn't understand 100% the method. Why is the inference time here so much higher for Marmol Coda than Camel? Because it sounded to me as if in the end you're also just an inference time evaluating a neural network.
No, no, oh, okay, sorry, there's a, maybe I should have called that another name. So inference, so it's at inference time, but it's not the time you employ to evaluate the neural network. It's the time you employ to adjust the task-specific parameter.
Okay.
So for the first two methods here, you do that by some gradient descent. So you adjust the weights by doing gradient descent, which is not guaranteed to converge. So it might take time. Whereas here it's just
OLS.
squares regression.
Yeah. Okay, cool. Thanks. And can I small follow up? Not follow up, but in the light now of your talk, I was wondering if your question for the previous talk was actually thinking if there's a way to do symbolic regression in a similar way
Yes,
to what you did here.
I think I saw a paper trying to do that. So they pre-train a neural network to learn some physical system, and in a specific way to they want to design the neural network so that on systems on same instances of the system but with different physical parameters, the weights of the symbolic regression can be tuned. So basically meta learning, but in a symbolic regression way. So that the previous talk made me think about that,
Yeah.
and I was wondering if you can combine cleverly a neural network and a symbolic regression. That might make sense, but I don't know much about that.
Okay, cool. Thanks.
Thanks.
Yeah, thanks for the presentation. I actually wanted to ask for a bit more details on the linearization. Because I guess, I mean, the way you show it, locally linear, it made me think about Taylor expansions, but I would think in that case, you have to worry about convergence radius. If not, if you're talking about like linearization of operators, I think of Koopman operators, but in that case, you have to worry about truncating the dimensions, right? So I guess just I'm curious a bit more details of the linearization.
So here the linearization happens with respect to the physical parameter, not to the state. So it's
Okay.
not as in Koopman operator where you assume that the dynamics is linear with respect to the state.
Right.
Here it's the given function with respect to some physical parameter. And so as I've mentioned before, you don't assume the physical system to have this structure, but you expect that if it does have a structure or a similar structure that is some approximate linearity, then this method is going to fit well because the learning model has exactly the same structure.
And what if the true dynamics models doesn't actually exhibit this linear structure? Then will it,
Then, well, you expect some lower performance and you might have to try some more expensive methods. But the point here is that if it does, that's a very cheap method to leverage that.
oh, okay. Thank you.
Much cheaper than MAML. I don't know if you've already worked with MAML, but it involves second order gradients, so it's very, very computationally expensive to train and also to adapt.
Okay. Thank you.
Thank you.